I would suggest that you pause this video and try these couple problems from earlier lessons. So hopefully after pausing and trying, you should have gotten the first one to be an inconsistent equation because the left side will never equal the right. And then in number 2, it first asks what makes the denominator 0, and so that value is 0. So that just means we never wanted x to equal 0. So then solving the equation, we should have come up with x equaling 14. Today we're going to continue more with section 1.3, which was all about modeling and applications. So we're still using linear equations to solve problems, and now we're also going to solve a formula for a particular variable. So let's dive into more of these word problems. It says in 2000, there were 39.8 million Americans without health insurance. This number has increased at an average rate of 1.7 million people per year. We're going to first write a formula that models the number of Americans without health insurance, Y, X years after 2000. So it's saying that X is that independent variable. So that means that that needs to go along with like our slope. And then Y is our dependent variable. Whatever X is, Y depends on that value of X. So in 2000, 39.8 million Americans without health insurance. So that's the flat amount that at that value, at that year, that's how many didn't have health insurance. So that's like our y-intercept. And then 1.7 million, that's how many have increased each year. So that's going to be our slope or our rate. So we're going to have y equals, we can put the 1.7x first plus 39.8. Okay, so notice how because it was increasing at that average rate, that's why 1.7 is positive. Had it said decreasing, then we would have wanted that number to be negative. So always keep that in mind as well. So now that we have that formula, it says use this formula in part A to determine the number of Americans without health insurance. Use the formula from part A to determine when the number of Americans without health insurance will exceed the number in 2003 by 8.5 million. Okay, so if we're talking about exceeding the number in 2003, we first need to know, well, how many had no health insurance in 2003? So hopefully we're okay with the fact that to go from 2000 to 2003, that's a 3-year time span, okay? And X is representing the number of years. So that's what I want to figure out first. I want to figure out in 2003, what's that number of Americans without health insurance? So we're going to have y equals 1.7 times 3 plus this 39.8. Okay, so we get to use a calculator. If I multiply and I start solving, I'll see that in 2003, we're at 53.4 million Americans that don't have health insurance. Okay, so now if it's asking, when will that exceed? Well, so I know that I have to figure out the year in which that's going to happen. So now we want to solve for X. So now I'm going to have 53.4 equals 1.7X plus 39.8. Okay, so now that's going to help us out. So I'm going to start by subtracting the 39.8. That's going to subtract and give us 13.6. And then I'll divide both sides by the 1.7. And so then that gives me a value of X to be 8. Okay, so that's how many years it's going to exceed the number in 2003 by this 8.5. So we are going to then add that on to the year that we're talking about, which was 2000. So 2000 plus 8 would be 2008. All right. I'm sorry. That number didn't come from this. So this equal, I'm sorry, I misspoke. That was 44.9. And then I added on this 8.5 because they wanted to know when it exceeded that. So that's where this number came from. I'm sorry, I misspoke there. Okay. So Moving on to the next one. It says the bus fare in a city is $1.25. People who use the bus have an option of purchasing a monthly coupon book for $15. With the coupon book, the fare is reduced to 75 cents. Determine the number of times a month the bus must be used so that the total monthly cost without the coupon book is the same as the total monthly cost with the coupon book. All right, so we're going to let X equal number of bus rides. Okay, so we're trying to figure out how many times you have to ride the bus to make the one equal the other. So we're talking about if I was just to use the bus fare versus if I was to use this coupon book. So we need to know what do each of those represents. Okay, so if I'm talking the bus fare, then like it says, it's $1.25 per ride. So that's why that needs to be multiplied by X. If I'm talking about buying a monthly coupon book, then you're paying $15 no matter what, and then each ride is just 75 cents. So that's the rate that needs to be with X. So I'm going to set both of those equal to each other. And then we're going to start solving for X. So I'm going to subtract that 75 or the 0.75X over to the other side. And that gets me 0.5X, still equaling 15. I'm going to divide both sides by this 0.5. And that tells me that X equals 30. So the bus needs to be written 30 times in that month in order to make it worth buying that coupon book. Otherwise, if you ride the bus less than 30 times in a month, then the coupon book is actually not saving you money. All right, let's talk about solving a formula for one of its variables. Solving a formula for a variable means rewriting the formula so that the variable is isolated on one side of the equation. It does not obtain a numerical value. So we're not dealing with, okay, I got to solve for this. What is it? X equals 2, X equals 5. No, we're just dealing with a bunch of variables, no numbers per se, and we just want one variable to be isolated by itself. So the most general formula that I can kind of have you think about is back in algebra when you were dealing with lines, okay? A lot of the times you wanted it to solve for y. You wanted it to say y equals, like our slope-intercept form, y equals mx plus b. All right, so since there's a y, an m, an x, and a b, we manipulated it to get the y by itself. So that's what we're going to do here. Notice that we're going to solve the formula for a particular variable. So in the first one, 2L plus 2W equals P. So that's an L, it's not a 1. Okay, so 2L. I want to solve for W. Well, if there's only one W in this particular formula, my goal is to start getting that by itself. So I'm going to first move the 2L over to the other side by subtracting, because 2L and 2W are not like terms. I couldn't combine those. So then that gives me 2W equaling P minus 2L. And then my last step, I just got to divide by 2. So W equals, you can leave it like this, where it's one big statement or one big expression. That's perfectly fine. If you wanted to, you could technically break it apart. It could be P divided by 2 minus L, because I divide both those terms, and 2L divided by 2 would just be L. So either one of these is correct. It doesn't really matter because they are equivalent. In the next one, we want to solve A equals 1/2 times the quantity X plus Y. We want to solve that for X. Notice that X is inside parentheses. So in order to solve for X, we have to get rid of the parentheses. There's a couple of different ways for you to go about doing this. We can definitely distribute the 1/2, but it's probably going to be a lot easier if we actually, instead of distributing, 1/2 is being multiplied by that entire parentheses. So how do you undo multiplication? You divide. Now in this case, because I'd be dividing by a fraction, it's the same thing as multiplying by the reciprocal. 1/2's reciprocal is 2. So I'm going to multiply both sides by 2. Because then notice that 2 times a half, that's just 1. So now I have 2a equals, and then I don't need the parentheses anymore if there was just a 1 in front. So then it equals x plus y. And so if my goal is to solve for x, the last step is to get the x by itself. So I'm going to subtract the y over, and so we'll have x equals 2a minus y. And that's probably the fastest way for us to solve. All right, so now it says, let's solve a formula for a variable that occurs twice. So all those other ones, we only saw the variable that we were looking for one time. That's not always the case. So when the variable you were trying to isolate is located in several places in the formula, you have to move that specific variable to the same side first. Then you'll factor out the term that they have in common, and then you'll continue to simplify. All right, so it says solve the formula P equals C plus MC, and we want to solve for C. So the nice thing about this is that we have C's on the same side already, so we didn't have to do anything to move them to the same side. So like it stated, after they're on the same side, I'm going to factor it out. They have a C in common. So then when I factor out a C, well, if I take out a C, I'm still left with something. I'm left with the number 1 if I was to distribute. And then I'm left with an M for the second term. So now that I factored out the C, it's back to the fact that C is being multiplied by this parenthesis. So how do you undo multiplication? Well, we divide. So I'm going to divide both sides by 1 plus M. And that gets me the C by itself. So C equals P over 1 plus M. I can't split this up because there's 2 terms in the denominator. Had it been flipped around where the denominator was the numerator and P was in the denominator, then I could split it up. But anytime you have addition or subtraction in your denominator, you can't split up the fractions. It can't be P over 1 plus P over M. That's not equivalent. All right, in this next one, it wants us to solve for R1. So notice that I only see it once as of right now. However, because we're dealing with a bunch of denominators, we're going to want to think about clearing away our fractions. So that means I need a least common multiple. Or at least common denominator, I'm sorry. And so because we are dealing with 3 very different denominators, because R is different than R1, which is different than R2, I'm going to then have all of them multiplied together to create that least common denominator. So I'm going to multiply every single thing by those 3 terms. So once again, hopefully you're okay with just following along. If I'm multiplying that least common denominator by 1 over R, the R's are going to cancel. So the numerator of 1 gets multiplied by R1 and R2. That equals the second fraction. R1 in the denominator is going to cancel out with R1 from the least common denominator. So the numerator of 1 is just being multiplied by R and R2. Plus, hopefully we're okay with the fact that the R2s are going to cancel. So the numerator of 1 is being multiplied by R and R1. So by clearing away the fractions, now hopefully you notice that R1 is in 2 different spots in this equation. And so because they're actually on opposite sides of the equation, I'm going to move the one from the right over to the left so I can get them to the same side. Now these are not like terms. So R1, R2 minus R times R1 cannot be combined. And then we'll still have R times R2 on the right. So now what do they have in common? Well, they have R1 in common. So I'm going to factor that out. That leaves us with R2 minus R in parentheses. That still equals R times R2. And now to get the R1 by itself, I'm going to divide by what I have in the parentheses. So R1 really equals R times R2 all over R2 minus R. And once again, because we're dealing with subtraction in our denominator, I can't split apart the fraction any further, and that would be my simplified answer. So I would suggest that you pause the video and see if you can solve for the variable that's being asked for. Once again, in problem number 2, those are L's, those are not 1s. So hopefully with the first one, you could do it several different ways, but the 1/3 needed to get moved over to the other side, either by dividing or multiplying by its reciprocal. And then to get the b by itself, I had to divide by h. In the next one, I wanted to solve for h. They were not on the same side, but there were two of them. So I moved the one from the left over to the right. I moved the term that didn't have an h over to the left. I factored out what they had in common, which was the h, and then I divided to get the h by itself. And then once again, because there's two terms with addition in the denominator, I could not simplify or break up that fraction any further, and that was my answer. So that's us using linear equations to solve problems as well as solve a formula for a particular variable.